Hello, everyone, and thank you very much for coming to this session about decomposing security vulnerabilities. A show of hands, how many of you implement security in your company or know a company that implements security in order to comply with regulations? And this is the current state at the moment. The security is perceived as a checkbox, and it is there primarily for compliance regulations reasons. We develop policies that contains various vulnerabilities each company is interested to comply with. Most commonly used are the OWASP top 10, which is OWASP's most cited document, and it's a little bit both of a blessing and a curse, especially since it was picked by PCI DSS as a standard, which is not. And then we develop these policies that contain all the OWASP top 10, because why not put them all? And then we run applications through various tools, static analysis, dynamic analysis, to see how those applications are against these policies. And then we get the reports, and the reports are sent to the applications security teams, and then to the developers. So how many of you are from the application security team? And how many of you are developers? So you both have been on this side. When you get now, you have large reports with lots of flaws that needs to be resolved in order to comply with the new policies. And this becomes a problem in particular in companies where there is a security gate and developers cannot deploy their software until those flaws have been resolved. And this is a problem when the focus shifts a little bit. So instead of actually focusing on the actual security of the application, the focus is on making these flaws disappear from the reports so developers can go and release their software. And this is when I get questions like, my application is behind the firewall, why do I have to fix the SQL injection? Or sometimes I have fixed the cross-site scripting. I have actually added a filter that looks for the word, for the tag script. So it's a shift now in order to get rid of these vulnerabilities and have the software release so they can focus on what they like the most, fixing the flaws. And the problem is that today we still develop a high large of insecure applications, and injection is still king. And this is the current state. In the latest OWASP Top 10, 2017, injection is still in pole position at number 1. And we have known about these vulnerabilities for over 20 years. The SQL injection was first mentioned in 1998 in Frag magazine. The term of cross-site scripting has been coined by Microsoft in 1999. So we know about these vulnerabilities for over 20 years. So the question is there anything else that we can do? Because if we continue on the same route and we do the same thing like we've done until now, we are at the risk of talking about injection for the next 20 years. A little bit about myself, who am I and why am I talking to you today? My name is Katy Anton. I come from a software development background. And this is when I got involved into the OWASP Top 10 Proactive Controls, which is a project for developer by developers, which should be included in every software development project. I currently work as application security consultant at Veracode, where I advise application security teams and developers around the world to secure their software. In most companies, the security posture is measured using the CWEs, which stands for Common Weakness Enumeration. And this is kind of a standard in most companies. So this is a formal list, which is a way to which describes the software security weaknesses which have been introduced in the software at architecture, and design stage and during the code development. And this is what all of these are, software security weaknesses. And they have been analyzed for a long period of time, classified, organized. There is a very nice classification on NVD website of all of these. And I will start my analysis with the most common category of vulnerabilities, which is injection. Now, the injection is still the most common vulnerability found in software applications today. As a category, it contains multiple types of injections. And you have command injection, cross-site scripting, code injection, XML injection, LDAP injection, SQL injection, just to name a few injections. And if we go a little bit further in details in each of these, then you can have further classification of all of these injections. For example, this is a classification of the SQL injection only. Now, you don't need to spend too much time looking on this graph, but the point that I'm trying to make is that now we are asking developers to think of all of these type of injections when they write the code, and that's not possible for them because their focus is on writing the functionality. So no wonder that we are still talking about injections today. So the question is there anything else that we can do? Can we look in another way at all of this? If we go back to the injection, and we just go to a very simple definition of what the injection is, just the basic, very basic one. The injection occurs when you have some type of data, which is then combined with a sort of a syntax. That result is then sent through a parser, and that's when it ends up being executed as code. So the data, which is not only from get and post, but also from a wide variety of sources like HTTP headers, file uploads, configuration files, data from the database. So when data from all these variety of sources is combined with a sort of a syntax, that result is sent to a parser, and when we want to store the data into the database, we send that result to the SQL parser. When rendering a web page, we send that result to an HTML parser or the browser. And that's when we end up with that data being executed as part of the code. I would like to take this view in order to focus more on the red part, the output where we end up with the code, with that data executed as code. And I'm going to flip it. So in the case of the SQL injection, we have the data which is combined with the SQL query that is sent to the SQL parser. And that's when we end up with the injection. The best defense for this is to parameterize the data before sending it to the parser. And this is the primary control, data parameterization. But as defense in that we still have to validate the input. The input validation helps to prevent vulnerabilities that a developer might not be aware of at the time of writing the code. A good example for this is the second order SQL injection, which is the injection where the injection payload is recorded and stays dormant in the database until it finds the right environment to be exploited. So that's why we need both of these controls, the primary defense and the defense in death, input validation. In the case of the cross-site scripting, we need to contextually encode the output to neutralize the characters that can trigger the code injection. But as defense in that, we still have to validate the input. And similarly for XML injection, code injection, LDAP injection, and command injection. So rather than focusing on all type of injections, which can be overwhelming for developers. And definitely I know from my experience that it cannot be done when they are writing their code. What we can do instead is to focus on these techniques which are familiar to there. And as a primary defense, we should always parameterize the data. If that's not possible, then contextually encode to neutralize the characters that can trigger the injection. And that's defense in that we still have to validate the input. The best point to validate the input is when your data enter the application in order to effectively reduce the attack surface. For example, in the case of an MVC framework, the best point to validate the data is in the controller. That's where the data enters the application. The next category of flaws that I'm going to tackle are the intrusion, or better said, the lack of intrusion detection. The problem today in most applications is that auditable events like logging, fair logins, high-level transactions are not logged. If there is any type of logging in place, then the format is not consistent enough in order to allow the operations teams to centralize all these logs, automatically process in order to get some meaningful information, intrusion information within a reasonable amount of time. So the problem boils primarily to two things. One is what is logged, and the second one is the content, the format of the logs. To put it simply, if a pen tester is able to get into a system without being detected, this is a good indication that that application or API does not have enough, it does not have enough intrusion detection mechanism. So the question is, can developer do something about this? For this, we have the security control, which is the security logging. This is a control that developers can use in order to log security information during the runtime operation of an application. According to the OWASP App Sensor project, which is a very good project, it has two parts. One is the a tool, and another one is the documentation, and this is what I'm going to focus on as part of this presentation. So according to the app sensors, there are considered 6 types of detection points which are good attack identifiers. And these are authentication and authorization failures, client-side input validation bypasses, whitelist validation failures, obvious code injection attacks, like for example, when you have obvious SQL injection payloads or cross-site scripting payloads, and a high rate of function use, when you have a high number of page requests in a very short period of time. So let's go a little bit through more in detail in some of these to have a better understanding of what exactly I mean. Now, in the case of the request, if an application expects to receive post, but instead it receives GET, this is a very good indication that somebody has intentionally intercepted that communication and has intentionally changed from post to GET. This is a type of anomaly exception that should be logged. Again, if the application receives extra form or URL parameters, a good example of this, and something that a pen tester will almost every time do, is to add debug equal true. If these extra form or URL parameters are detected on the server side of the validation, this is another type of exception that should be logged. In the case of authentication, if the application expects to receive, for example, 2 parameters, username and password, but instead it receives only one of them, the username, because the password has been removed, that's another type of exception that should be logged. Again, if the application expects to receive, if the application receives extra parameters during authentication, and something that a pen tester again will try to do is admin equal true to see if he can escalate privileges. If this is detected, this is another type of exception that should be logged. In the case of input, now, if the validation on the server side fails, despite the fact that there is a validation on the client side, a very simple example of this, you have a form. In one of the HTML forms, it has an HTML attribute of maximum length. However, when that string reaches the server, it is greater than the length defined on the client side. Now, this is a very good indication that that since that data has left the client where we had the maximum length behind, somebody has intercepted that communication, intentionally changed that string and then sent it to the server side. So this is a type of exception that again should be logged. Or another one is when the validation on the server side fails for non-editable user fields, like hidden fields, checkboxes, radio buttons. A good example for this is you're on an e-commerce website and on the shopping basket. If there is a hidden field there for the price, that's very tempting for somebody to start playing with. And if the value of that field is, when received on the server, is not the one that is expected, that's another example of a high-value transaction where that anomaly should be logged. So, these are just what we are actually doing. We are just ensuring that the server receives what it expects to receive. But by putting these exceptions into place, what we are actually doing into the application, we give the software the mechanisms to respond to these possible identified attacks and reduce them or even stop them, depending on how we choose to respond to this when we do the coding. So if we are to recap, a basic workflow is that every time we have data entering our application, we should validate it. And that's not only from get and post, but also from configuration files database. Any exceptions should be logged. Any output should be contextually encoded, and every time we send data to the database, we should parameterize the queries. So this is a basic workflow that not only that will prevent a large portion of the injections, but also give the server this ability to respond in real time to these possible identified attacks, the ones that we have identified and we have chosen to respond in a manner to them. Another type of category that I will tackle is the sensitive data exposure. And for this is about the data both at rest and in transit. Now, when it comes to data, we need to ensure the confidentiality. The data cannot be spied on. Integrity, the data cannot be changed, and availability. There are several types of data depending of the type. So when we have data at rest, then we have the type of data where we need the initial value, like credit cards. These must be encrypted. Then you have the data where you still have to store it, but you don't need to know the initial value, like, for example, the user password. This must be hashed. And then you have data in transit, which must be encrypted over a secure channel. When it comes to encrypted data at rest, a challenging part for developers is to actually store securely the key that is used to encrypt the data. And this is an example from an application that we discovered during a code review, where in a folder, in the same folder, we had two files. In one of them, we had the encrypted password, which we kind of guessed what the encrypted password contained. And the other one was entities. And when opened, it contained a seed, assault, and iteration, which turned out to be used in conjunction with the password-based key derivation function 2 to generate the key that was used to encrypt the data. So to put it simply, in the same folder, we had both the encrypted data and also everything that you need to do in order to generate that key. Happy days for everyone getting access to that folder. And this was a new application where the team has tried to come up with their own homegrown solution of storing the keys, which is definitely something that you shouldn't do. So when it comes to data at rest, when you need to encrypt it, the best cryptographic algorithm out there is still AES, but it is important to store the key away from the encrypted data. Stay away from the homegrown solutions because they so easily can go wrong, and use dedicated key management solutions. But it's also important to define a key life cycle. And we need to have in place a mechanism to replace those keys. Because if the key has been compromised, then you need to do that one anyway. So it's better to have in advance defined a process. So when this happens, you know exactly how to do it, and you have it documented as well. When it comes to data in transit, we are getting pretty good at sending the data encrypted over a secure channel between the client and the application server. In particular, thanks to Let's Encrypt, we are getting pretty good at this one these days. But we still have a problem between the communication behind the firewall, like, for example, between the application servers and other non-browser components like the database. And this is where we have to improve as well. So ideally, when you transfer the data, it should be over a secure channel throughout, including behind the firewall. And the next type of vulnerabilities that I will tackle is the third-party components, or using components with known vulnerabilities. We're getting pretty good, and there are lots of tools out there to check for vulnerabilities in software components and open source software components. But the problem that I see from the discussions with developers is actually doing something about that list. You end up with a pretty long list of all type of vulnerabilities. And that's where it's the problem, actually doing something about it. And the type of software that has these problems is the type of software that no developer wants to touch because he's afraid that if he touches in one part, something will break. So it's easy to break. You might do one change in one bit, but you don't know where it will break. It's difficult to test. As a result of all of these problems, nobody wants to go there and do any upgrades. And all of these lead to technical debt. So the bottom line is that all of these issues are because of an application that have a high level of technical debt, or so in some cases, legacy applications, which there are companies where they have quite a large proportion of these. So what can we do about this? Before answering this question, I'm going to introduce another concept, and this is the attack surface, which the attack surface, as a simple definition, is the sum of the total points through which a malicious actor can enter data into or extract data from a system. And in security, we have a very simple principle, which is whenever we do, we need to minimize this attack surface. So this is the entire purpose of this. And that's what we should do. We all should achieve to do as well when you're bringing external libraries. So I'm going to take 3 examples of this scenario, of these 3 components. One of them is an open source library, like a logging library, which is something a developer would almost every time do. The logging is something that they will bring in. Another example is a vendor API. Because again, these are external components, and despite the fact that it's a partner, we have to remember that these days there is a trend where rather than attacking the main target, the hackers choose to attack a vendor, a partner of the main target. So we need to treat this one as an external component as well. And the next example is when you're bringing another library from another team within the same company. And this happens a lot in large companies where you have one library that is then used through multiple applications. So I will start with the first example. When bringing in a logging library, this usually, because it is ready-made, it has a large number, a wealth of functionality, and highly likely that your application is not going to need the entire functionality to be used. In the case of logging, you are likely to use only 3 levels like debug, warning, info. So for this scenario, when you want to expose into your software only a set of the functionality and you want to hide unwanted behavior, a good design pattern is a simple wrapper. What this allows you is, so if there is data flowing through that one, having this wrapper, this interface, it helps you to control the data that you expose. And if there is a vulnerability, then you know exactly what you expose into your software. And at that point, at the interface points, you have that one point where you can put extra controls if needs be. But also, very importantly, so this is a way to reduce the attack surface. That's one of the benefits. Also, very importantly, this is a design pattern that helps you to easily upgrade or even replace obsolete libraries without much penalty. The other example that I'm going to look into is a vendor API. And for this, I'm going to consider the case of a payment gateway, which is common in e-commerce applications. And it's highly likely that in an e-commerce application, you are going to have more than one payment gateway. So for this scenario, also it is, you have several partners and each of them have their own endpoints. Highly likely your application will have its own transactional method. So for this scenario, when you need to convert from the provided interface to the required interface, a good software design pattern is the adapter design pattern. This helps to convert from the provided interface, so wherever the partner endpoints are, to what your software needs. Also, you can have multiple adaptees at the same time, so it's easy to switch between them. So if a partner becomes breached, then this will allow you to quickly get into control of your software and remove that partner. And the third example that I will give is the scenario when you use in your software a library that has been developed by another team within the same company. A good example for this is the single sign-on, which is quite commonly used in many companies this day. And it can be quite complex. So this package can get quite cumbersome and quite complex. So for this scenario, when you actually need to simplify the interaction between a complex subsystem and your own one, you can use the facade design pattern. Now, this is a very good one as well for legacy applications. It simplifies this interaction between your own software and a complex subsystem. So you can use it as well for legacy applications. And it's again another type of design pattern where the facade gives you that one point where you can control and you can see what's exactly exposed into your software, and it helps you out with the upgrade. So if we are to recap, a secure software starts from the design, from the point that you have chosen how you are going to bring a system, a library, a package into your own software. From that point, the security of the software starts. So you can use a simple wrapper when you want to expose into your software a set of functionality and you want to hide unwanted behavior, then you can use the adapter design pattern when you want to change from the provided interface to the required interface, and the facade for legacy applications. I think it's worth pointing as well that this works very well on the server side, where you can actually hide functionality they would not apply on the client side. The last one that I would like to tackle is the environment configuration, and we see more and more of this. So we can, as developers, tackle this one during development, during deployment, and after release. Now, during development, ideally you would have, as developer, you would use the same users as in production. For example, the database user that is used in the development environment, it should have the same permissions as in the production connection. And the application user used on the development environment should have, again, the same permissions. And ideally should be a dedicated one. So if your application should access certain folders using only, for example, read permission, which would apply to configuration files, for example, then this should be in the development environment as well as in production. So they should replicate as well in the production. During deployment, we should ensure that these permissions still apply. And for companies, this can be achieved today using infrastructure as a code, but if this is not available, because it's not that modern application, we can still achieve the same thing using a set of bash scripts for critical parts of the system that we want to check the configuration for. And again, after the release, ideally you would adopt a configuration manager and ensure that you provide scanning, continuous scanning across all the servers to ensure that the configuration is still preserved in place. So rather than what I would like you to take away is that rather than focusing on these CWEs, because at the end, all of these CWEs are software security weaknesses, which we can measure only after the software has been developed. Let's focus instead on the security controls that prevent them are familiar to developers, and they can be used from the beginning. And also, in order to be effective, this should be in place every single time. So we cannot say that we validate this data, but we can't validate that one. We are not going to validate it. Ideally, it should be for every data that enters the application. And both of them should be used like the primary controls or defense in that in a consistent manner. Because we have to remember that an attacker needs one flaw to bring down a system. As defenders, we have to defend everything, and that's why it's important to use them consistently. Also, we need to verify for them that one, they have been put in place, but they have been put in place in a correct manner to be effective in preventing the software security weaknesses. So every time the data enters the application, we should validate it, and not only from get and post, but also from data from the database configuration files and other sources. Any exceptions that we get during the validation should be logged to give the software the mechanisms to respond in real time to the possible identified attacks, the ones that we have identified. Any output should be contextually encoded, and any time we store data into the database, we should parameterize the queries. If we need to access a command on a system, ideally you would leave that one as a last resort, because sometimes you can achieve the same thing using other methods like a library. But if you really, really need to access an operating system command, then you should parameterize the data. Every time we bring in a new library, not only an open source library, but also from a vendor, an API from a vendor partner, or a library from another team within the same company, we should choose a software design pattern that helps to reduce the attack surface, and also it helps in the long term to easily upgrade those components to actually stay on top of the technical debt. Any time we store the data, we store data, we need to store the encryption key away from the encrypted data in dedicated key management solutions. And every time we transfer data, it should be done via TLS, not only on the public facing, but also behind the firewall. And we should ensure that our configuration is the same that we intended and adopt the configuration management and have this continuous scanning of the servers across the network in order to detect any misconfigurations and remediate them. Now, if any of you is looking to improve the security of their own applications, these are some security controls that can help you with that. And because there are security techniques that are familiar to developers, it's also easier to achieve compliance. A developer is highly likely to say that that flow cannot be exploited. It happens to me all the time. But is unlikely to say that they cannot validate or they cannot parameterize once they have been shown how to do it correctly. Even more, you can actually involve them and have them check between themselves. This can be done during the code review, peer code review, to ensure that these basic security controls are in place and are okay and are implemented correctly. This allows you, as an AppSec person, to free you up of time so you can focus on other more complex security issues. And this is just a way to handle things. You don't need to stop here. Because, for example, if you want your policy to change it and you want to have added to it a new vulnerability. For example, the new entry of the OWASP top 10, which is the A4 XML external entity, or in other words, the CVE 611. Now, the security control for that one is to harden the XML parser. So you can add that security control to the list for developers of what they need to do. And you can have that one added as well into your policy. And hopefully, using this of focusing on the security controls will help us not to have the injection still in pole position in the next OWASP top 10. Thank you very much.
And there is definitely time for questions. I've got a microphone for somebody who wants to ask a question. I'll go up front.
Thank you. I was trying to see the relevance of validating the input that the data comes from the database. Shouldn't the data be on the trusted common base or TCP?
Okay, that's a very good question, because I am asked a lot of it. Now, the database is a device on your network, on your private network. Keep the microphone.
Yes, please.
The database is a device on your network, private network in most of the cases, but you don't know who is on a private network. So I'm also OWASP chapter leader, and we have people from red teams. Their feedback, which do ethical hacking, their feedback is once they get into a company's network, the security controls are minimal. And we have had breaches for this. The most famous one is the Marriott data breach, where the attacker has been on the network for over 4 years. You don't want to be that company where the attacker has been there for 4 years and your software was not able to respond to these type of things. So that's why it's not considered usually trusted.
Yeah, but it's already on the database. You have greater problems, right? I mean, if it has data or he has access to the database or can change the data in the database, you have bigger problems than the input in the application, right?
So for example, a good example of actually validating the data for the database when you actually use the data to create dynamic queries, SQL commands, where you have that data into locations which cannot be parameterized. So that's why you need to validate it. Because if that happens, then you don't know how that data is used. And unless you actually do a risk analysis, what happens, and you analyze the entire software where that data from the database is used, because if it's used on connecting to other devices, that's when you are going to have the problem. So that's one of the problems. You consider trusted. Don't trust anything. Just put the security controls every time. Because in this way, we just make it more difficult for the attackers. We are never going to get a 100% secure system, but it's just to put them off of hacking a system. Okay, thanks.
And another question, we've got time for one more, I think. And if not, then I'm going to say thank you. Thanks, Katy.
Thank you.